more than this, and I'll be taking you to some Google Docs that are in the queue for becoming tiles fairly soon. So that same link is right here, the What's a Microcontroller for Python and the Microbit. For your homework, you all went through certain selections from software setup, writing programs, and communicating with the terminal. And I hope that went well for all of you because we'll need it today. And then today, what we're going to do is start in breadboard setup and testing. Okay, so let me make sure I'm on track. Yes, I forgot to mention the prerequisites versus the main lesson. So let's go back a second here. So the writing microbit programs is what I had you do a little excerpt of each one. And that was part of the homework. And that's part of the prerequisites along with the setup for the microbit and working with the terminal. And so then the first of the main lessons is basically putting the kit together, but there's a number of lessons built into that that we'll get to experience as we go here. And so that is, that's what I'd like to talk about next. And what we'll be doing today is setting this system up and running some of the tests that will actually have the students go through. So the first thing I would like you all to do is you've already got your microbit and USB cable out. Oh, pardon me. So first of all, some of the things that the students will be exposed to are one, what is this breadboard thing? And so there's some nomenclature that goes with a breadboard and some how it works stuff. And one example is that this particular breadboard has 3 bus strips, each with columns of sockets. And coming back, here's the breadboard. There are terminal strips, 2 of those, which is where most of the circuits are built. And each of the terminal strips has letters and numbers that allow you to basically pick out a row and a column to say, hey, go to the G16 socket. So that's one example of something that they will be exposed to along the way as they're putting this together.
You sunk a battleship.
Yeah, exactly. I can't tell you how many times I had that same thought as as I was going through this. And for those of you who might not remember that from 1970s advertising by a toy company, there was a game called Battleship where you could not see where your opponent had put the ships on his grid. And so you would start calling out numbers and find out whether you hit something or not. And the big catchphrase was, "You sunk my battleship." All right, so this is the first thing I would like you all to do, is to fish out these items from your kit. And by the way, let's see, I'll paste this link in so that you can look at it on your screen if you need to. Chat. Paste. Okay, did that come through?
No, I didn't see it.
I got it on my side.
Okay, that's because for some reason, I think I received a chat from Chris, and so it set me to reply only to Chris. There we go.
Now it's there.
All righty. So this is the page. You can even get most of the animated GIFs also have higher res MP4s. And so, for example, if you need to stop, and this is either while your students are doing it or possibly in some cases while you're showing it to them, you can stop. And for example, we've got our magnifying glass here, and in a second, we're going to put it over and make it clear. And this moment right here, where I've stopped, shows where the pins underneath the microbit should be lining up with the row and column, basically column A rows, looks like 11 through 30. And then there's a couple pins on this edge adapter that also go into this bus strip. That's some of the new nomenclature that was just visited. So everybody, please open up your box and grab these parts and go ahead and put them together as shown.
Question for you, Andy, while they work on that. So we may have omitted the piezo speaker from the kits, I'm not sure. But okay, we did. Thanks. So we show code adjustments to use the onboard microbit speaker?
Yeah, was this because I used an outdated screen capture in my slide that still had the piezo in it?
Maybe so. So it's by intent there's no speaker then?
It's by intent there's no speaker.
Thank you.
Yeah, the plan is to use the
Perfect.
microbit 2's built-in speaker.
The chat is full of applause. Thank you.
Oh. Excellent. And then if I could get folks to give me a thumbs up or a when they've got everything connected. Looking good, Neil. And Kelly, very nice. Thank you, Sarah. Ed's thumbs up. Oh, thank you, Charles. Oh, Charles is funny. Charles, try putting it in front of your shirt so that it doesn't, there we go. It was being grayed out by the background. Thank you, Kenneth. And what I'd like you to do is it looks like, I'm guessing everybody's ready. So give me a shout out if you're not. Otherwise, I'm gonna keep moving here, and please just, like I said, unmute yourself and tell me, hey, wait a second, slow down, I'm not there yet. So one important thing that I added to this animation for the students is right here. I'm gonna play this for you. So I really wanted to drive home that those pins need to sync all the way into the breadboard. So I'll play it one more time. So we go sideways, shows the side view, and the pins syncing all the way in. I've seen a number of tech support calls where the students simply had not sunk it all the way into the breadboard first. Okay,
Andy?
so yes.
Quick tip, maybe you want to put a little rubber bumper on the back of the microbit. It doesn't have to stay on there. It could just be underneath it, just to keep it from bending, because it's very flexible now, and it will bend off the board if you lean on it.
Yeah, that's true. Okay, thank you. I need to start taking notes here. Okay. The way I imagined it was that actually the student would be kind of doing it like they do when they just have the microbit and a battery or any other thing, because that they normally put their finger underneath it and then press on the top with their thumb. But we'll take a look at ways to make that more bomb-proof.
I taught middle school too.
Yeah.
Getting a nod, that's good.
All right. Next up is okay, so now that we've got that set up, the next thing we're going to do is set up some probes. And along the way, what we talk about by way of introduction is, hey, this breadboard thing you've got, it's got rows. And each row of 5 sockets allows you to connect wires to each other. So if you're in a different row of 5, you're not connected to the wire in the other row of 5, like there. Those are 2 different rows of 5. So are those. But those 2 are in the same row of 5. And we go through some examples so that the students get a better idea of, hey, what's connected and what isn't on a breadboard. And of course, there's also a trick where you can plug a jumper wire across 2 rows of 5 to make it a row of 10, or actually 8 if you count the pieces you already used. Now, how many of you are new to a breadboard? Do you want to go through this a little more slowly, or did that just make sense and you're ready to move on with the understanding that rows of 5 are the way to connect wires together? Okay, I'm seeing a number of thumbs up. All right. Again, if this feels unfamiliar or if you want some clarification, just stop me. Otherwise, this is the lesson where students learn how to connect 2 wires or leads together. And I hope that this support is better than what you've seen previously in tutorials, because I've always felt that quite a number of tutorials were lacking on this topic, both my own and others in the industry. There are also 3 bus strips on your breadboard, and all the sockets are interconnected vertically on individual bus strips. If you go to another bus strip, they're not connected unless you use a jumper wire to connect them, in which case then they are connected. Okay, so this is going to start over again. All right. Here's our breadboard. In addition to those terminal strips we just talked about, it's got 3 bus strips. And those 3 bus strips can be used to do vertical connections as opposed to the horizontal ones that we did with the terminal strip. And so these are some examples of, there's 2 columns there. Each column is connected unto itself, but it's not connected to the other column, nor is it connected to a different bus strip. But you can go ahead and use a jumper wire to connect the bus strips together, and then 2 wires, like those 2 black wires in the sockets next to bus strips with blue sockets, will end up being connected. Are we still good? Thumbs up, thumbs up. Okay. And like I said, I'm always happy to take a shout out and slow down. All right, so the next set of parts that we're going to have you gather, speaking of support, I'm hoping these drawings are nice and clear. I'd like you all to grab the black and the red alligator clip leads from your kit, along with 2 black jumper wires, 2 3-pin headers, a red and a blue jumper wire. And I think I'm going to leave it on this slide right here. Because it shows the 3-pin headers and where they're going, and the alligator clips. I think I'll play along from here as well. And remember, there's always an MP4 that you can open up to take a look at these animations and stop them at certain points. Okay, I am caught up. How's everybody else doing? Thumbs up. Oh, I still see a few heads down though, so I'm going to wait for a second here. Oh, good. Thank you for the chats. And then there's Ed. He probably went through all the chapters and is patiently waiting for us. You're muted, Ed. All right, looks like we're getting closer. Okay, hold on. There's a URL that just came through, but I don't recognize it. Oh, that's the URL to the slideshow.
Yeah, we have one person who's catching up.
Ah,
A
okay,
few which had trouble getting in, so I'm giving them the YouTube link.
got it.
I think you wanted 1 PM Pacific, not 1:30 on that slide, right?
Oh, yeah, I sure did. Thank you, Ed. And thank you also for the other editorial catches. We might want to have you start commenting directly in our documents if you're interested.
Nice thing is that ends,
That'd be
this ends
fun.
at 5 on the, in the Midwest and 5 o'clock somewhere.
Okay, so how's it going? Are we all hooked up and ready to start measuring continuity? Okay, so the next step is on the script page. I'll paste that into the chat. Okay, now on the script page, we'll need you all to go to this page. And then we'll have you download this continuity tester.hex. Now, if you just click it, it's probably not going to work the way you're hoping. What you'll need to do is when you get to the page, again, I put that page in the chat. We'll want to have you right click and then select Save Link As. Okay, so that's how we always download pre-written scripts. And it will ask you where to put it. And your downloads is fine, especially if you have it sorted by date modified to show the most recent. Then as soon as you download it and then go to your file browser, which came up on the other screen. So once you download it, you can go in your file browser to downloads and it'll appear on top. Another handy spot that it appears in Chrome is right down on the bottom left here. And so, so after this, some of you may have realized that there's a little animation that's showing what the next steps are. And you basically go to python.microbit.org, hit the load save button. for it to restart. Okay, so right-click continuity tester.hex, save link as, and you'll save it. And then it's going to be on the lower left there. And then open python.microbit.org in a new tab. And then click its load save button. And then drag continuity tester into the gray box in the load section. And that'll open it for you. You guys are having better luck than I am here. There we go. My computer's slowing down, I think, because possibly because of the temperature in the office and the video processing demands that are being placed on it.
It's not a grease.
Hello?
Greasy.
Oh, okay.
Answer. Blue.
Okay, how are we doing? Have we all got this? Because the next thing to do is to hit connect.
There was a question or request to repeat that series of steps, Andy.
Ah, okay. So let's go back to this page here, and I will open up the animation of it. Oh no, I don't have the animation posted on this one. Okay, so right-click continuity tester.hex, save, and it's going to appear in the bottom left of Chrome. Then open python.microbit.org in a new tab. Go over to that tab, click load save, drag continuity tester into the gray box and drop it. And that should open the continuity tester script in your microbit. Then click the connect button and go through the connect routine, followed by flash to load it into the microbit. We'll do that one more time. Right-click continuity tester, save link as. It'll go to your downloads, but it's also in the lower left there. Then right-click python.microbit.org, select open a new tab, go to that tab, click load save, and then drag continuity tester from where it is in your downloads into the gray load box. And that should open the script in your Python editor. Then click connect.
It's not a greasy.
And then click flash. Okay, messages.
Thanks, Andy.
Excellent.
People have trouble with these steps, we could stay after and give you a hand too.
Just a
Oh,
quick
thank
question.
you.
We're following your basic one. We're not looking at the one that's under learn for electronic measurements.
Well,
It's wired differently. There's an LED and resistor and such. So I wanted to just confirm.
okay, let's see here. Where we are right now is backwards a little bit from the measurements chapter. So if I go back here, here's electrical measurements. We are still in breadboard setup and testing. And so in electrical measurements, we do change the circuit around considerably. But for the first step, we are currently in first connections with a breadboard, and we're about to just try to measure and verify that that certain rows are connected or not. And so now that we've got our continuity tester loaded into the microbit, which I need to catch up with you on here. Now that's interesting. It's telling me that this initial flash might take longer. You may have seen this when you first started the homework too. It happens when a microbit gets connected to the online editor for the first time. What it does is it updates the microbit runtime so that it's ready to work in lockstep with this particular editor. If you go back and forth between, say, make code, which is another one of the editors, you'll see that the first step will take longer there too, because they make code puts a different runtime onto the microbit. Okay, so what we're doing is first of all, just a really basic test to do two separate rows. And you may or may not hear a beep, but when you are on separate rows, there will be a little not connected symbol. And when you're on the same row, there will be a little check mark to indicate connected. And this is an activity where we want students to probe the breadboard and see that either connected or not connected, the connected circles, the not connected circle slash or the connected check mark. All right, so mine is finally ready, and let's go ahead and take a look. Okay, I'm going to switch over to the camera here, stop share. Okay, can you guys see me? Or can you see my board? Can you see my hand waving in front of the board? Okay.
Yes.
Alrighty. Okay, so currently,
Pun intended.
thank you. So currently, we've got the circle with the slash indicating not connected, because we started, as the instructions said, with one wire on row 16 and the other on row 17. Then going in and unplugging it and putting them both onto row 17, we get the connected check mark.
You know, it's cool, Andy. You have your scan lines that are actually showing that thing flickering.
Yeah,
Oh,
it's like
that's
we're getting a raster effect.
Yeah, it's really cool because it's slow, you know.
but can you even tell that there's in the thumbnail, now that I'm looking at it, I can't see that it's a check mark. Can you
It's a
guys
check
see
mark.
that?
If you follow the tracing of the matrix, you can see that it is the check mark. And this is
wow.
kind of nice because with this, you could actually emphasize, look, it's a trick for the eyes. how the LEDs are operating in the matrix.
Now, both Mark and Neil are showing me nice, solid, clear check marks. I need to find out what kind of cameras you guys are using, because I think I might go shopping for one.
You gotta buy an expensive Microsoft tablet to get that.
Oh, okay. Yeah, unfortunately, I have one and its camera doesn't work.
Oh, no.
Yeah, there was an Intel update, and ever since that happened, the camera became a not feature. Anyway, all right. So
Well, I have a Mac laptop and it's functioning fine. You can see no raster whatsoever.
Here.
even on mine,
No, on yours I can see plenty of raster.
yeah.
In fact, when you disconnected it so it wasn't connected, I didn't know what the heck was happening there until I really scrunched my eyes.
Okay. Well, I'm glad that you guys can see it right in front of you instead, because that's much better. And thank you for showing us your check mark. And can say, could you also unplug one of those wires and show us the little, there we go. So that's the little not connected circle slash. Very good. Thank you.
Andy, just so you know, there's Windows settings where you can tweak your camera's refresh rate from 50 to 60 hertz, and it should make that go away. It's a Windows setting. We found it out during distance teaching when like lights would flicker. You got to go change it to 60 hertz.
That is incredibly cool. Thank you.
That's amazing.
Yeah, Windows settings.
There's something new every day, right?
That's one of the greatest things about the workshops, actually, is that yeah, it's a great place to exchange information. And I have to say that leading a workshop, I think I take away as much as you guys do attending it. And I try to feed that back into quality materials for you guys to use. I'm hoping you like what you see so far. Could we just get a real quick discussion on how you feel about those animated GIFs and the and measuring a pair of measuring the continuity of
The probing thing will be nice for the students to conceptualize like what's actually in the breadboard rather than seeing the abstract pictures of like a disassembled breadboard, but actually like getting the immediate feedback. I think that'll be nice.
I agree, and I was hoping that would be your impression, but since you mentioned the disassembled breadboard, let's see here, where is it?
I did peek ahead. I saw that.
Okay, yeah.
That's a cool picture. I like that. And I was thinking I would use a very fine marker and just draw a line for every 5.
Yes. Let's see. I need to switch over to share again, because I almost made that mistake where I started talking and was looking at my screen. All right, so here we are.
That's great. That's an excellent picture. That's 1,000 words right there.
Yep. Yeah.
It's pretty much almost the same that I was using for my controls class.
Yeah, and it's a pretty common picture. I thought this was kind of a nice angle, so that is in support of the measurements. And how are you guys if we just skip past the rest of the continuity measurements? I'll point out that here they are, and it's the next page from where we were on. And the idea is that students will have the opportunity to basically, earlier we looked at a video clip of bus strips and how they were connected. And then we looked at a video strip of terminal strips and their interconnections. We looked at a clip of bus strips and their interconnections. And what this particular page does is it has them go through every single one of those variations that was shown in the animations. So they're actually testing every pair of probe points that they saw in the animation. And on the left here, I hope you'll see that it also shows how the microbit will respond, whether it shows a check mark or a circle slash when you have it connected and continuity either is detected or is not.
Just a little thing, as an IT type of person, we use continuity checkers for verifying that an Ethernet cable actually has all the 8 pairs conducting electricity. So that's the kind of device that this is sort of echoing in its design.
Yeah, that's true. It's really interesting because continuity happens. I'm glad you mentioned IT because I don't always think about IT. And yes, with your Ethernet cables, you're definitely checking continuity, although those testers are rather sophisticated compared to this. Because they often tell you, oh, 10 meters down, there's a kink in the cable, because they use some pretty sophisticated signaling. Other places where continuity becomes a thing is troubleshooting printed circuit boards, especially in manufacturing and repair. That's a very common use is products that have maintenance staff, be they radio transmitters, receivers, exercise machines, automatic door openers in supermarkets. They all have people who will go and perform these kind of measurements as well. And so
Auto shop, don't forget auto shop.
Oh, that's right. There were so many times I did continuity measurements on my stupid blinkers on my 60-something Ford Falcon that never quite worked right.
Yeah. Wouldn't be without it.
Yeah, that is so true. So auto mechanics, definitely another one. All right.
Hey,
Well,
Andy, one thing I'm noticing here is that the sound is commented out.
That's true. This is a purely visual video because the animated GIF, you can't get sound, but we have had a number of discussions of saying, hey, what if we add sound to the
Well, you'd want a continuous sound. I mean, I uncommented just to fool around to see what it would do. But I mean, most continuity testers, at least off of any meter, the sound is continuous. That's what a student would normally see.
Oh, I'm sorry. I thought you were talking about overdubbing the clips. Okay,
no, I'm not. I think you can get enough out of this. They can figure this out. I'm just talking about the script itself.
Yeah, had yours toned once and then went to the no symbol?
Right. It would tone once, but that's all you'd hear. Whereas normally on any test equipment, it'd be continuous tone.
Yes, it would. I actually intended it to be continuous tone, so I will take a look at that between today and Wednesday.
Yeah, I'm not expecting it to be in the gift or show, in what you're showing on the screen. I don't.
Got it.
I think that'd be a waste of time to.
Yeah, no, it should be continuous. I'm not sure why it's not. I can tell you that the online editor changes the way the microbit responds in response to certain bugs that are reported. And so that may have either gone away or just needs to be a bug that's reported so that they can, or it may be a bug that I hid in the multimeter module. So,
Well, Andy, I was going to say, I don't like your tone.
Andy, I think it's music.pitch. You have 3000, 100, the 100 milliseconds.
Oh, it's me.
Why it's toning.
Yeah.
Get rid of the 100.
Okay, so, well, let's see here. The thing is, I would expect this.
And then you've got to write a code to stop it in the else statement.
Yeah. Okay, good. I'll rewrite this. Yeah, that's my fault. All right. Yeah, fortunately, I won't have to report any bugs this time then. Okay, good. So I'll let you guys know when that's updated. Excellent. Thank you. All right. So what is next? Going back to our day here, we just did first electrical connections. I should mention that there is a how it works page that immediately follows it, and it mainly is talking about the script. And I was already there. Okay. So there's a how it works. Try this. Okay. So after try this, there's usually a how it works and a your turn. So this talks about the script and how it works. And then there's usually a your turn where we ask the students to do a little bit more. And I'll show you another example of that. This one doesn't have it. Okay, moving on to electrical measurements. So we are now going to try out the voltmeter feature. I got a heads up that the resistance measurement feature is not behaving as expected. So we're going to skip that for today. I'm going to take a look, and we might run back and do that on Wednesday. Again, voltage measurements is one of those things where there's a lot of kits out there now where you can either build a robot or build some circuits that do cool things, but oftentimes they keep it qualitative and they skip the quantitative stuff like measuring voltage. So what I'd like you guys to do is to try it out with me. And incidentally, there's always a cover page to these things. So when you go to electrical measurements, it's going to show you the most relevant diagram that was found in the text. And then it's going to explain what it's about. It's going to give you a link to the kit that we're using here. It's going to tell you if you need to do anything before coming here, and if so, what. And then there are also some curricular goals at the end. And then we jump into activities. So here's the top page, and then each of these headings with a little triangle next to it is an activity that you can click to expand. And then within each activity, there's sections to work through. And the sections follow a pretty consistent pattern of, well, normally parts. I'll use measure resistance since I guess we're using all the parts that we already got out. So I'll try measuring current. Darn it. Well, I'll show you that later. Normally we have parts before script and tests. Then there's a how it works. And yeah, I'm just batting zero here. I will come back to this once we get to LEDs and talk a little bit more about the pattern, because it's a little bit specialized here in some of these earlier activities. Although it is, oh, I see what happened. So they put, I leave it in a Google Doc and then it gets posted. And so what happened is that the cover page here, measure voltage, has the parts and circuit. Sorry about that, folks. And one thing I did is made sure that if there's a new part that a student hasn't worked with before, that I show them the a picture of the part and its schematic symbol. And then we go ahead and build it up. So I would like you guys to grab a green LED, a red, brown, gold 220 ohm resistor. Again, that's red, brown, gold, and a jumper wire. And you know what? I feel like I skipped ahead here. I did. Okay. Electrical measurements. We, oh, geez, sorry about this, folks. I'm going to backtrack. We haven't put power on our board yet. So breadboard setup and testing. I finished first electrical connections. We didn't get to set power for the circuits. How are we for time? We've got another half hour. Good. Okay, so pardon the hiccup. I got way ahead of myself. So the next parts we need are 2 red jumper wires and 2 black ones. So everybody go ahead and grab those. And then we're going to have you connect them as shown on the screen here. And this is a point where I tell the students, if I'm working directly with folks, to be careful, because we don't want to, for example, accidentally put the red wire from 3 volts to the wrong socket. If you're 1 socket off, you could end up shorting out the system and causing the microbit to shut down to protect itself. I will also text you this so that you can potentially look at it on your computer too.
Just very quickly, I noticed that I have my breadboard upside down. I have the ABC on the bottom. So that's why I only notice it now, because I see the plus and the minus, red and the blue, transpose on my system.
Okay, now just to check, is the color of your IO edge adapter black or blue? So that's this part right here, if you can see my thumbnail.
No, I can't tell from your display. Let me
see here.
Was it,
I mean, it'll work the same, I think.
Well, no, the if this part needs to be black, if it's blue, then let's see.
I think I'm black.
Yeah,
I'm
you
black.
are.
Okay.
Okay,
All
good.
right, so
The blue is an older version that had the pins backwards. Yes, it'll work fine if you follow the rules of electricity when making your connections. Or you can go ahead and just quickly rebuild it, since we're not too far in yet. And that is your call. Am I broadcasting my breadboard?
yes.
Okay, is it visible? Is it clear enough?
Yeah, it is. You might want to rotate it. I know your document camera reverts to you being upside down usually.
Yeah.
It's okay. I think everyone's okay with that though.
Can I loop back to that blue and black edge adapter
Yes.
conversation? Both Amy and I have the blue ones.
Oh.
And they are not going to work, or they will work fine? They're just backwards.
They'll work okay. You just have to swap a couple of wires. So let's see, I need to share my screen to get to this. Share screen, screen 2. All right, so if you have the blue one.
Yes.
Just put the black wire in the red socket, and the and then you'll be okay. It's basically these two are swapped. Also, Ken had something to say about that.
Yeah, so if you have any of these blue adapters, I'd prefer to get them out of your classroom. And so that you only have black adapters, which does a bunch of things. It gives you the current hardware and avoids us having all these notes in our tutorials. So if you have blue adapters, send me an email and I'll replace them with the new black ones.
Okay, thank you.
Sure.
That is really cool. Okay. See if I can zoom in by one more increment. Guess that's as good as it gets. How's the view?
Perfect.
Okay, and did I remember to chat you this page?
Not sure.
Okay, I'll do that now. Okay. So again, we're just adding 4 wires here. One from the 3V row to a socket in the column next to the red stripe in the center bus strip. And then we're going from a socket next to the blue stripe on the left bus strip to a socket by the blue stripe on the middle center bus strip. And then we're running a red wire from the red column on the bus strip from the center to the right. And then we're doing the same with the blue column going from center to right. And be careful with that one. And how are we doing? Has everybody got that wired up? Excellent. Seeing a lot of thumbs up. I do see. Okay, sorry. I thought I saw the top of the head, but the head was nodding. So, all right. So, by the way, there was an animation of this too. And I did some close-ups, hopefully to help the students really double check. And then in the checklist instructions, it's saying, hey, check those close-ups for each of those connections and make sure they're all correct before you plug in that USB cable, which incidentally, I should have told you to unplug the USB cable, but I didn't hear anybody saying that any blue smoke came out of any devices, so we're good. Now let's download the next script. It's measurevolts.hex. I'll give you the page for that. Have you run to it and download it. Paste. Okay, it should be in the chat. And again, you want to right click and select Save Link As. Okay, so Ken, can you see my thumbnail and let me know if now I'm right side up?
Yep,
Okay, so I was upside down before?
yep.
All right.
I hope all the blood didn't rush to your head.
It kind of did, actually. Got a little bit of vertigo there. But it's passed, thankfully. Okay. So do we all have measurevolts.hex? We're going to go through the same thing. Oh no, it's going to be a little bit different. So heads up, everybody, onto the screen. I'll show you from mine. Okay, so I'm after downloading measurevolts.hex. So right click, save link as. Measurevolts.hex should appear as a tile down at the bottom. Okay, then go to python.microbit.org and oh shoot. Okay, so on Windows you can just drag it into the editor and it'll update. But if you have a Mac, you'll need to hit load save and then drag it onto the gray box in the load area as a way to open it. So I don't know what Chromebook does, but either one of the, I think it's probably going to support the drag it right onto the editor pane. But if it doesn't, go to load save and drag it onto the load box. And then once you've done that, make sure you are connected and then hit flash. Now, although you don't technically need to be connected to hit flash, opening Serial, you need to be connected. So we're going to open Serial and then take a look at the volts. And the thing to do is to use your black probe, plug it into a socket by a blue column, and then use your red probe, your Alligator Clip probe, and plug that into a socket by a red column. And we want to verify that it tells us that there's about 3.3 volts sitting on those volts of electrical pressure, so to speak, across those two columns. So I'll go ahead and do that quickly by plugging mine into a red column and a blue column. And hopefully it's visible that my voltmeter now says 3.29 volts. And if I put the Alligator Clip probes on the same column, it says 0 volts, or very close. Thank you, I agree.
Damn it.
Uh-oh, frustration. Everybody doing okay out there? Okay, 0.62 volts is not the expected value. Yeah, there are built-in A to D converters in the microbit, and we're using those. We're actually taking the A to D measured at the black Alligator Clip and subtracting it from the A to D measured at the red Alligator Clip. And what that allows us to do is to get a very real voltmeter style measurement. Because, for example, if you reverse your probes, you might get negative voltage. For example, I'm going to reverse my probes so that the black probe is plugged into a red socket and the red probe is connected to a blue socket. And lo and behold, there's negative 3.3 volts.
So Andy, if we built the one with the green LED, we're looking at least on mine, I've got like 1.98 volts. Is that because the way that you've got it triggered is it's reading after the pass-through voltage?
Let's see here. I'll connect an LED real quick. If I understood correctly, you're saying that the LED is pulling down the voltage across the rails?
That's correct. As soon as I remove my LED, then I go back to my 3.26. So what it does is with the LED, at least in this configuration, is it's not giving me the 3.26, roughly as it takes and gives me the remainder after the pass through.
I'm building up the circuit.
It's cool because it also explains to students why, like, that there's power that's being consumed.
Yeah, thing is, yeah, okay, so I have a light connected to the, if you can see my screen now, I have a light connected to the power rails, and it is on. By the way, we'll get to this, but so right now I've got the light connected, it's on, but moving back to, and I have the probes so that here's the negative probe, and I'll go ahead and put the positive one so that it's easier to see on the red, right? So here is the LED's power. This is the positive 3 volts line. And then here is the negative of the LED, and it's glowing. And so if we probe here and here, we should see that the 3 volt supply is still being regulated. And on my screen, it's saying yes, that I still have 3.29 volts. It didn't vary at all. Let's see, I'm not sharing the screen.
That's because your setup is slightly different than the one that was online, where you've got the positive is coming in right after the anode of the LED, and you're taking it off the rail. When I swoop it that way.
Right. Sorry. Okay. Yeah. So going back to undoing the share, I was just about to share screen. So you're saying that we're measuring the drop across the resistor right here? Is that right?
Drop across the LED. So leave your ground where it was. Now take your positive and move it over just one column over from there. Now you should be getting that 1.98 roughly with the drop of the green.
That's right. So now we have a 2 volt drop across the green LED.
1 point something. Yeah. And you can see I'll experiment here in a second, but we'll probably see it'll be different with different LEDs as well.
We will. Yeah.
Manufacturer.
Yeah. And those are all upcoming lessons. So sorry, I thought we were looking at a bug.
Nope.
I'm a little bit shy about that because one of the attendees let me know that there was a bug which I was able to verify in the ohm meter. So something changed recently. So we're going to skip the ohm meter today, but we'll hopefully find a minute or two to quickly do that on Wednesday. Let's see, we have 13 minutes left. We're doing okay.
It does make that drop change with different colored LEDs, which is cool.
Yeah. Yeah, and we get into Ohm's law, both measurements and calculations. I'm going to have a question for you guys on Wednesday about a simulator I'm interested in bringing into these tutorials. It's an online simulator that does not require any membership. Fallstat, if anybody recognizes that or already uses it in their classes.
Say it again, please.
Oh, Fallstat is the, I wasn't ready to show you that today, unfortunately. Let's postpone that because I don't want to go on a search for the for the website. But I do plan to show you a simulator that is kind of cool. I like it because there's no membership required. It's just a free resource to run circuit simulations, and it's also a little bit more grown up than some of the others that you'll see that are shooting for the younger crowd. I think for the particular level that we're writing for these lessons, that we want something that's a little bit closer to, an industry style circuit simulator.
Quick question, if that's okay.
Oh yes, please.
So in your code, you just have this function voltmeter, which I'm assuming is something from one of those 2 imports. Is that something that's accessible to see so students could, quote unquote, create their own tools modeled after that or not?
Oh, so cool. Yes, it totally is. Let me share my screen. Share. Yeah, so I'm a little bit behind on publishing the API for the module. But when that gets published, it'll be even easier. Okay, so can you see my screen okay?
Yeah.
Okay, hit load save. And then this is familiar, but one thing we haven't talked about is the show files. Okay, when you drop down show files, you'll see multimeter.py. And then you can hit the download button of that. And it'll warn you that it's a script that your computer might execute, but clearly there's not anything malicious in this one. And then once you've downloaded it, you can actually just right click and duplicate your Python editor and then drag multimeter.py right onto the, or you know, just open it the same way you would open the hex files we've been opening. Come on, there we go. So this is the entire module. And so yes, they can absolutely open it and customize it the way they want. And there's really even some opportunities for them to customize the multimeter software that we're going to look at next as well. Did that answer your question? Are you okay? Does anybody want me to repeat that sequence?
That's fantastic. And then the last thing, and this might just be a dumb question, so I apologize, but like in all of your function definitions, you have pin 2 and pin 0. Are those hard coded or is that just a normal value? I'm not as good at Python as other languages, so I apologize.
Yeah, no problem. So MicroPython for the microbit has objects that are named pin 1, pin 2, pin 3, pin 0. And let's see, I need to get back to some code where it's close serial. Okay. See, I'm going to stop the share. So the first part of the answer to this question is that currently, do you see how the circuit has the alligator clips connected to P0 and P1 here, and P2, pardon me?
Yeah.
So we've got our little 3-pin headers, and we've got the alligator clips connected to those. And so currently the multimeter object is going to use the pin 0 and pin 2 objects. And it's actually, I talked about the multimeter subtracting. Trying to make my taskbar go away. There we go. Okay, so that voltmeter function is right here. And so it is set to default to pause equals pin 2 and
Wait,
neg
hold up. Can anyone else see the
pin
screen?
0. Hello?
See your screen, Andy.
Huh?
We're not
Are
looking
you,
at your
are
screen.
you watching me just talk at you?
We're
Share
watching your
screen.
circuit talk at us.
All right. Okay. Is this any better? Now, first of all, did everybody see when I hit load save and then did the show files thing? So like here we have the measure volts and we've got load save, show files, and then we want to download multimeter.py. Okay, and say to keep it since it's an executable that Chrome is a little bit worried about. And then you can go ahead and open it up by dragging it into, so then I right clicked this and duplicated the tab and then dragged multimeter.py into the tab. And so we were looking at the voltmeter. This is the voltmeter function right here that gets called by the main script right there. So this is the main script. Very simple for the students. And then inside and then we have from multimeter import star. And inside the multimeter script, this is the voltmeter function that they call. And right now I have pin 2 as the positive and pin 0 as the negative, since I have the black alligator clip connected to P0 and the red alligator clip connected to P2. But let's say that we wanted to use P1 instead. Well, I could actually, in the function call, say pause equals pin 1.
And so all those pins are defined in that microbit library, is that true?
Okay, so about well, it goes a little deeper than that because there are certain pins that are built into the microbit that have A to D features. So for example, if we take a close look at, where would I find this? If we take a close look at the edge adapter, see how there's a little squiggle next to P0, P1, and P2?
Mm-hmm.
Okay, that squiggle is the symbol on the edge adapter for analog, that it has the analog feature available. And then I'm going to real quickly see if I can send you a link to a nice little document about that. The first thing is to use help. So you can click help in the editor and then select documentation. And if we want to talk about input output pins, that's right here. And so this will give you kind of a fairly nice explanation of, you know what, I'm not seeing, I don't know why this came up. I think input output pins. This isn't where it was at yesterday. I feel like they scrambled the links a little bit, or maybe I'm just not looking for the right thing. Hello world. Images. Okay, yeah, these tutorials changed a little bit, I think, just recently. So I'm going to go a different route here.
We'll link to the edge connector descriptions.
Yeah, that's where I'm going. Here is the edge connector full pin out. So this is a more comprehensive list of what each pin does. So here we have P0, that's pure analog in. P4 shares with the LED column, and that has some special considerations there that are explained later in the document. But so you have 6 analog in pins, and 3 of them that we're using have no special considerations. The other 3, you have to disable certain things in order to get them to work in code. And so let me send you this because it'll be helpful. Chat. Somebody already beat me to it. Yeah. Or, oh, it's a slightly different resource. Let's see what Alan sent. This is, oh, it looks the same. Yeah, okay. Yeah, all right, same document. Okay, good, thank you though. All right, so that is measuring volts, and we've got a couple minutes left, but this is kind of a nice stopping point actually, because we took some voltage measurements, and oh, I see some discussion here about different, is Logically a simulator? Logic.ly?
Yes, it's basically got logic gates and circuits. You can build different things in logic.ly. It's free. You can just hit the demo version. There is a paid version. I'm not sure what the benefit is exactly.
Okay, let me see if I can find that Fallstat site. Let's see here.
There's the Fallstat site up.
Okay. So this is the one I'm interested in because it's free. It's there's a full screen version too. Let's see here. Full screen version. Here we go. Okay, so so this is the circuit that was built, and I like the way it kind of gives you a general idea of the direction and amount of current that's flowing, and it graphs at certain nodes, and it lets you place parts and do all the things you normally do with a circuit simulator. Yet it's free. It's a web app. It does have some interestingly professional features. Like there we go. I just went ahead and closed the switch, and that's going to change the behavior of the sine wave. And I'll open it again, and it went back to its previous dance. And so this is something I'll go ahead and paste it in and have you guys take a look at it. Tell me what you think. I'm definitely leaning toward it. I'd like to use this because you can even save files and open them with the app. And so that would allow us to share some files. Oh, thank you for asking. What is the homework today? The homework today is going to be, I'm going to email it to you. There are 3 items. One is to get 2 new alkaline AA batteries, AAA batteries, pardon me. 2 new alkaline AAA batteries. Then let's see where we are in the slideshows reckoning of things. Looks like I might have closed my slideshow accidentally. Please. Recent. And hopefully we're back. So I'm open to some suggestions here because we could go one of 2 directions. We could continue with our measurements, but I kind of want to maybe just briefly touch on measurements and then jump into building the lights. So yeah, let's okay, so what I'll do is I'll take a tour of some of the measurement stuff that is covered without going through it step by step at the beginning of the next session. And then we'll go into building lights. So the other thing that I'm going to email you for a homework assignment is going to be, we'll have you play with, these tutorials on your own to see how you feel about the overall pacing and support images and etc. Like if you're on your own doing it without a guide, how's it working for you? So basically we're going to do, we're going to just basically connect 2 LED lights and run some scripts and try them out. And I'll, yeah, let's see here. Does that look like enough, everybody? I think that's a good homework assignment. Get your AA batteries or AAA batteries, and then build a couple of lights and get them blinking. And I'm actually going to also, I want you to try measuring them with the voltmeter and then with the oscilloscope. Okay. Okay, so I'm checking the questions now. So apparently Mira had a question that is being echoed.
It was
Okay.
answered for us already.
Oh, okay. So yeah, if you have the batteries that came with your kit, then just make sure they're accounted for. There should be 2 AAA batteries that came in your kit. Now, if you are one of the attendees that opted not to receive a kit because you already have microbit 2.0s, not to receive a microbit 2.0 Go bundle, then make sure to hunt down 2 new AAA batteries. And then, like I said, we'll have you, I'll send out the homework assignment shortly after this, and it's going to include just some basic following these tutorials, because I'm hoping to collect feedback and adjust accordingly based on what you observe as you go through the tutorials. And this is a really good spot to do that. So I'm going to ask you to try these tutorials, and then also the oscilloscope and voltmeter measurements. And so then we'll reconvene Wednesday, and we'll continue on into push buttons and then servo control. And then on Friday, we'll finish with the analog. I guess I tacked it on to Wednesday. I don't think we're going to get all the way through, but we'll go to potentiometer, and then we'll do some extra projects as time permits on Friday, and then do the curriculum tour. And that's it. Shall we switch to open question and answer session?
Andy, I've got a question. If I pull the lead, one of the leads off, and maybe you mentioned this and I just missed it. It doesn't go to 0 volts, it's 0.64. And obviously that's something to do with the A to D. Is mine working correctly?
It probably is. I'll have to take a look at that. They've got some built-in pull down resistors, and it may be that there's just a slight offset in ground resistance over the distance. So that you may have a little bit of ground or a little bit of resistance between where your probe is still plugged in to ground, and then the ground that is being pulled with the 100K resistor that's built into the IO pin.
Okay. No, what I was saying, you're right. If I plug it into ground where they're both, I guess what I was referring to, if I pull, let's say, the red probe off, so the red probe is not connected to anything.
Yeah, it's floating.
So it's still measuring a volt, 0.64 volts, which have to be the offset in the A to D.
Yeah, and I think that's the case.
Yeah. Okay. It wasn't something I was expecting. I guess I would explain it to the students that way.
Yeah, it's true, because it's not exactly like a real voltmeter. It's as close as I could get.
I granted, but these questions, it's just like the other stuff I found.
Yeah.
I'm trying to head off the questions before I have the questions.
Yeah, and by asking them to me and us, it gets it so everybody can look at it and think about it.
Mm-hmm.
I felt like this went pretty well overall, especially that it seemed like I didn't have to really switch to an actual live camera view very much. And that's something that I'm hoping for. I want to be able to use the existing student documentation as opposed to saying, okay, here, I'm going to show you how to do it because the documentation isn't usable. That's not something I want to be the case. So I just wanted to check with you guys and see how you're feeling about what you saw with the documentation and how, if I'm looking for any suggestions because we're busy posting this to the web right now. And the thing I want to try to do is ensure student success as best I can. And so this is definitely the time to submit your comments. On Friday, I'll even talk about volunteering to put comments into some of our working documents. Which you'll also start experimenting with on Wednesday, because we're going to go into stuff that our web team is currently taking from a Google Doc and placing in the web pages that you worked out of today.
As a side question, what did you use for your graphics and animations?
What I used was a combination of CorelDRAW, Microsoft PowerPoint, and Camtasia. So the drawings are in CorelDRAW. For example, this drawing right here was done in CorelDRAW. We have a fairly extensive library, and I like the way it allows us to have a lot of control and make things super clear. The drawback is it is kind of cumbersome to use. So I'm thinking about it, possibly over time transitioning to some CAD software, but I want it to be nice and clear and visible like this. And until we get something that is an improvement on this, I don't want to switch. So then when extra labels were needed, I found it to be quicker to do that in PowerPoint. And then basically I took screen captures and Snagit and then stuck those into Camtasia and then used some of its effects. For example, if we go back to, let's see here, breadboard connection. Let's see, I think it was right here. Yeah, so it was, I think it was, we're close to it. There's the what's a breadboard, and then there's the connections. I think it should be at the bottom of this page. No, it's right here. No, those are the parts. Okay, so here we go. So so then I played some tricks, like you'll see that the whole thing rotates in a second. It's coming up real soon. You'll see it. Oh, we've got the close-ups first. That was in CorelDRAW because Snagit didn't do so well. None of the other softwares did it correctly. Those magnifies. That flip right there was kind of an animation trick where it's not really the same as in 3D rendering. It just kind of looks that way. But I feel like the effect was fine, and maybe some students will want to do it slow motion to see if they can catch the actual animation trick as opposed to the 3D rendering version. Okay, any more questions?
Not a question, but a comment on the continuity file.
Yeah.
With the music tone, I think you're going to run into interference because you are running the continuity function off of port 0 and the tone happens off of port 0. So when the tone happens, it automatically triggers no continuity because it opens up to the piezo buzzer.
Okay. What I might be able to do though is I might be able to get it to where it's at least beeping 3/4 of the time.
I could get it to beep once while active and then like do a little longer time and then turn off when it was there and then get it to beep again when it was on. So I could do it set with a break.
Okay. Thank you. I will try to take a closer look at that. I think that, did you already go inside the module to adjust it there?
No.
Or are you still, okay, so,
I was just playing around in Python.
okay, yeah, so you're at the top level. I think maybe if I go inside the module, I might be able to get you some better continuous beep.
Yeah.
You can probably just have an if statement that if one of the pins is active, then go ahead and send it and trigger the other pin. And that way you don't run into the conflict.
Yeah, the other thing would be, I might want to just stick redo the continuity tester so that it's on pin 1. My product and documentation manager is looking at me askance with that's a lot of work look on her face. Well, we found a bug.
Well, you decided to not include a piezo buzzer in the kit.
I know. And now
this is streamlining.
Andy,
yeah.
Andy, it's a lot simpler if you just blame it on Tommy because he didn't show up for this first one.
Oh, Tommy, there we go.
Oh, man.
Well, we're not recording. I'm talking with some of the group still.
Oh, okay. I don't know whether to call you the straight A students or the miscreants over there.
The answer is yes.
No.
They said the answer is yes. All right, so I'll take a look at that. My hope is that I can just play a trick by switching back and forth between. Okay, so there's only a few instances during that second when the continuity is being measured. And I'll have to take a look and see if they put some diode protection in with the speaker. Because, yeah. All right, well, anyway, I'll definitely look at that and let you know on Wednesday.
Michael, it's only a thumbnail, but man, he looks like you.
Oh.
The baby.
Yeah, there you go. Is that young Michael there?
This is Lucas.
Hey, Lucas. How you doing?
Alan, did you do the T1 workshop way back when?
I did. Charles, is that you asking? Or who's asking?
Michael was asking.
Oh yeah, I did the T1 back in was that Connecticut we won?
2017, that's where I remember you from. He was only 1.5 then. Now he's 5.
Wow.
Oh.
Let me don't let me go.
All right, go. Somebody needs to go to the playscape. All right, we're out.
Bye.
Bye.
Thank you all. We'll see you Wednesday.
See you Wednesday. And then, oh, by the way, feel free to email me if there's any afterthoughts you've got.
Yeah, see you Wednesday. I gotta run.
All right. Thanks, Kenneth.
Thanks a lot. Trying to clean up the room here for a new computer.
Oh.
Thanks, Andy. Bye.
Oh.
I think this documentation, Andy, is great. I mean, compared to the stuff with, the Bobot and all that, I mean, there's more than enough here, in my estimation for the student that they could work, because that's, my homeschool people are doing more on their own.
Yeah.
So this, it's not the same as a classroom, although I'm working to change that now.
Yeah, and in a way, I feel like it is. I mean, I feel like regardless of whether it's the classroom or a homeschool situation, if it supports a homeschool situation, it's going to support a classroom.
Yeah, my biggest thing, the biggest problem I have with homeschool, at least in certain cases, is speed of access on the internet.
Yes, okay.
I have people who are on dial-up, and that's unfortunate, but it's the way it is.
Yeah.
I'm fighting with my internet company now over their recent price hikes. So
Yeah, well, that's also a thing when we get to the oscilloscope usage. I'm concerned that not everybody's computer is going to be able to handle updating the display.
I tried that out. It worked. I mean, it worked all right on mine, but I mean, my system, you know, is a high-end system, so.
Yeah, there are several, basically, I managed to narrow down a bottleneck. I managed to find where a bottleneck could occur. And so now what I have to do is add some code to detect if the display is behind on updating the oscilloscope data, and then start dropping data and display a little message saying, you know, hey, maybe you want to think about going to a smaller time per division. Because that's basically if you get too many little dots that you're plotting, it takes too much time. And if the dots are coming through rapidly, each time a new dot comes through, the old ones have to be redrawn. And so that's a thing where I have to add something to catch that potential problem. In the meantime, the tutorials are going to say, hey, it's really important to drop your time per division to below this level before connecting. Sorry, I kind of jumped ahead here, you guys.
Oh, but that should be fine. I mean, the idea is this is not a scope. I mean,
right.
What we're trying to do is give a basic tool and show people, you know,
what it's like. And what they can learn using a scope, you know, what they can insight into a circuit is my main hope.
Okay, that's fine. No.
Okay. Yeah. So really, for the meantime, the instructions are going to say, important, set your time division to this, because otherwise your browser tab might freeze and you'll have to close it and reopen it. And then oh boy, oh, okay. Yeah, so anyway, that's I have 30 new messages. There's a whole bunch of chats. Is that everybody saying goodbye? Yeah, okay. All right, good. And then, yes, I have to check for some messages coming in through Parallax. Stop share. All right. So let's see. I need to make sure I've remembered. You mentioned that there was enough material for your homeschool group, Ed, and that let's see here.
Well, they can work on their own. I mean, the stuff that they can look. There's a difference in the two student groups. Okay, the homeschool students are they're different than the school group. Okay, you know, without disparaging anybody, they're just their education level at where they are is higher, is further along.
Oh, okay.
Okay, you know, so for example, I don't run into problems with, you know, basic math. Oh, you didn't learn how to do this. They come to me, they're a little bit, their grade level is higher.
Okay.
First, I'm trying to be, you know, trying to explain it in a way that I understand. I mean, their grade level is higher. Most of them are reading, you know, their reading scores are several grades above where they're at.
Oh, I see. Okay. So, all right. Okay, so I am being called away to another meeting. So I'm going to have to Sorry about that. I'm going to have to shut down the meeting.
I'm being called away too, because this is.
No.
Well, that's a 4-alarm emergency right there. We lost you muted, Ed.
Saying this is dinner time on the East Coast. I know you fellas are still early out there on the West Coast, but this is,
True.
It's 5 o'clock somewhere.
it is, it is right. It's past 5 o'clock here. Time to hoist the flag. All right.
All righty.
Hi all, thank
You
you.
folks have a good afternoon and evening, and we'll see you on Wednesday.
All righty.
Thanks a bunch.